Hello, I'm Seema and welcome to part 12 of the chapter Chemical Bonding and Molecular Structure. I'm now going to tell you about the valence shell electron pair repulsion theory. The valence shell electron pair repulsion theory was given by two scientists in 1940. The names of the scientists were Sidgwick and Powell, and this theory, there were some additions made to it by Nyholm and Gillespie, and this was done in 1957. We abbreviate the name of this theory, the valence shell electron pair repulsion, are abbreviated as VSEPR for the names, and it is commonly known as the VSEPR theory. Since you cannot pronounce VSEPR for the sake of convenience, we pronounce it as VESPR. So we pronounce it as Vsepr Theory. So the Vsepr Theory, it had certain postulates. And what were the points in this theory? Let us study them one by one first. This theory, if you look at the name, it talks of valence shell. That is the outermost shell of electrons in an atom. Electron pair, it means it pairs up electrons. And when we did the Lewis structures, if you remember, we made pairs of electrons. The lone pairs and the bond pairs, if you remember that. So it says that in the valence shell, the electron pairs, they repel each other. This is the basis of this theory, that electrons are present in the outermost shell and they are the ones that participate in bonding, and these electrons are paired. They may be bond pairs or they may be lone pairs. That is, bond pairs are the electrons which form bonds with the neighboring atoms, and lone pairs are those pairs which do not participate in bonding. And it is the repulsion of these electrons which gives specific structures to molecules. So let us read these points one by one. The shapes of molecules, they depend on the valence shell electron pairs. It is understandable. The shapes of molecules, now which atom are we talking of? Whose valence shell? The valence shell of the central atom, right? For example, if you have water, the two hydrogens are on the sides, oxygen is in the middle. So we are talking of the valence electrons of oxygen. So the Vsepr theory applies to the central atom in a molecule. And the arrangement of the remaining atoms which are bound to the central atom around that central atom is predicted with the help of this theory. So he said that they said that the shapes, they depend on valence shell electron pairs. And what is it that determines, what is it that leads them to have these shapes? It is the repulsion between these pairs. It is the motivating force here is the repulsion between the electron pairs which are present in the valence shell. This repulsion, when there is repulsion, what would happen? If you don't like a person, what would you do? Or there's a certain food that you really repel, you just can't stand. What would you do? If the moment that food comes and someone brings it under your nose, oh, just try the aroma of this. Would you like to take the aroma of that food, or would you just step back and move away from it? So repulsion causes them to keep as much distance as they can from each other. So that is the driving force. So electron pairs, the second point is that they repel each other. And if they repel each other, what would they try to do? They would try to occupy minimum spaces or positions where they experience minimum repulsion. You have two friends, you're a group of 10 friends, and there are two of them who don't get along with each other. So what would you do? If you're on a picnic, you're together, would you make them sit together? Would you make them eat together? Would you make them play together? And would you let them spoil the entire picnic because they kept fighting among each other? Or would it be wiser to just keep them on two separate ends? Let one be here and let one be here. Let's all enjoy and let them not come in contact directly with each other. Right? So that is what happens, that these electrons, they try to occupy a position of minimum repulsion, or you could also say that would be a position of maximum distance from each other. Wherever they can occupy this position of maximum distance, they would try to occupy maximum distance from each other. Then the fourth point is that valence shell is imagined to be a sphere. Now, I took this ball to explain this to you. They imagine the valence shell to be a sphere. And all these electrons are present in this sphere. Unlike the knowledge of S and P orbitals, this theory does not consider the orbitals of the electrons. It only takes electrons as pairs, and the only categorization it has is the pairs of electrons that are bound, that is bond pairs, and pairs of electrons that are not bound are called lone pairs. It does not talk of the S or P orbitals. It imagines all electrons to be identical and occupying the surface of the sphere. So you can imagine the electrons, which are the valence electrons, are on the surface of this ball, and this is your picnic field where you went for the picnic, and all the friends are here, and they repel each other. So what would they do? Two of them, actually all pairs repel each other. So they would try to occupy maximum distance from each other, and if they occupy that maximum distance, that would be a state of maximum stability. And in chemistry, when we talk of maximum stability, it means minimum energy, right? So he said that valence shell is a sphere and electrons are on the surface of the sphere and are at maximum distance from each other. And when we talk of, it's not just single covalent bonds that would be present in a molecule. You can have multiple bonds, you can have double bonds, you could have triple bonds. So he said, the theory says that, I'm calling the theory a man because it was given by 4 people. So I can't, when I say he, I don't mean any one of these. I mean the theory. A multiple bond is treated for all practical purposes. If there is a multiple bond, an atom is here and one atom is here, and they share not a single bond but a double or a triple bond, they would still be there and here. So a multiple bond is treated as a super covalent bond or a super single bond or a super pair. A pair of electrons is a covalent bond, so this would be known as a super pair. So you could say that a multiple bond is a super pair, and if you have resonance and more than one structure representing a molecule, then the Vsepr theory should be applicable to each one of those structures of the resonating, that is the canonical forms. It should be applicable to each one of those structures that you imagine. So these were the statements of this theory. Now, what was the difference? What was it that Nyholm and Gillespie had talked of? This is what Sidgwick and Powell had talked of. They only talked of bond pairs. They did not differentiate between lone pairs and bond pairs. So, when Sidgwick and Powell, they gave the Vsepr theory, they imagined the structures to be very symmetrical. On the other hand, Nyholm and Gillespie, they noticed that these electron pairs are of 2 types. They are lone pairs and they are bond pairs, and they also do not have equal repulsion. The lone pairs tend to show a greater repulsion to lone pairs. So the repulsion by lone pairs is the maximum, and then comes the repulsion of the bond pairs. So when you have electrons which are arranged around on the sphere in the atom, if you have 2 lone pairs, the repulsion between 2 lone pairs would be maximum. Then would come the sequence would be the lone pair repulsion is the maximum. Then a little less than that is the lone pair bond pair. If there is 1 lone pair and 1 bond pair, then the repulsion is a little less than lone pair repulsion. And if you have just 2 bond pairs, the repulsion between 2 bond pairs is the least. So why was this important? Because when Sidgwick and Powell gave their theory, all molecules had very symmetrical structures. But in reality, molecules do not have absolutely symmetrical structures. There was distortion in the angles or in the structures. That distortion could be explained on the basis of this imbalance in repulsion. If there was more repulsion between lone pair and lone pair, the distance between those pairs would be more. And if you had bond pair, the distance between them would be the least. So this would cause molecules to be distorted. Having understood this, now let us apply this theory and understand the shapes of molecules. I've made this table here. The first type of molecule is the AB2 type, where you have two atoms surrounding the central atom, right? So if you have two atoms, two pairs, when I talk two atoms surrounding, what are the number of, it means these two atoms have two bond pairs. Now whatever examples we have right here in this table, these are molecules which do not have lone pairs. We will first start from simple and then move on to more complex structures. So these are molecules which only have bond pairs, and we'll come to the lone pairs later. So these are molecules which have very symmetrical structures. Now you have two pairs of electrons around the central atom. You should imagine the central atom to be in the center of the sphere. They're right in the center of the sphere, the central atom, and the electrons are now on the surface, right? So electrons are all occupying the surface. In the center of the sphere, imagine it to be like a seed of a fruit. That center is the central atom. So at what angle should these two pairs of electrons be so as to have minimum repulsion? Maximum distance that two atoms can have among themselves around the central atom is 180 degrees. Any other angle would be less than this 180 degree. Therefore, when you have a molecule where you have AB2 type of a molecule, the geometry would be linear if there are only bond pairs around the central atom. Examples of this type are beryllium chloride, BeCl2, and mercury chloride, HgCl2. And the shape of this molecule would be linear. So AB2 type of molecules have linear structure or a linear geometry. Let us now come to the next type of molecule where there are three atoms around the central atom, and the central atom is A, and the surrounding atoms we assume them to be B. So the molecule is AB3 type. How would you expect three atoms to surround themselves at a maximum angle, at a maximum distance from a central atom? If you imagine this, the maximum distance that they can achieve would be that of a triangle. Just see, if this is the central atom, then three atoms should be along the three corners of a triangle, and along the three corners of the triangle, if you have them, each angle is 120 degree. Each angle is 120 degree, and the central atom is here in the center, and such a shape would be called a triangular planar structure. It is a triangular planar structure. Now, or it's also called a trigonal. It has three corners, so it is trigonal planar or triangular planar structure. An example of this type is BF3, boron trifluoride. I'll just wipe this off. Yeah. So, if I have to make the structure of BF3, now look, I have joined the corners to show you the structure of the three-dimensional structure of that thing that we have made. Now, the triangle, if you have to make just the bonds for the sake of ease, how would you write BF3? BF3 will be written as B, write an F here, an F here, and an F here. So, we're just making the bonds, and the rest of the structure can be imagined, right? So, the next molecule is AB4 type. In AB, if you have four bonds around the central atom, if there were three, we knew it would be a triangle, right? If there are four, the easiest thing that comes to mind is, why not have a square, right? if having 3 atoms around the central atom would make a triangle, and that is the best, the maximum distance, so your natural inclination would be to imagine a square, that the sphere is here and these are 4 corners, and you know, all these ends, these corners are actually on the sphere. I would like you to imagine there, if it's a square, it is 1, 2, 3, 4. You are imagining all of these on a sphere. So, if this is a square, you would imagine this to be a square. But in a square, what are the angles? What are the angles around the central atom in a square? In a square, the angles around the central atom are 90 degrees. Each angle is 90 degrees. But in the triangular planar structure, what was the angle between each of these? It was 120 degrees. Do you see? It was 120 degrees. So what do we see? Instead of having an angle of 90 degree, if this structure, instead of being planar, we make it in 3 dimensions, and we imagine that this triangular planar was there, here, and one bond comes out of it, and one bond comes out of it here. Yeah, the triangular planar, and one bond is coming out of it like this. But what happens when one bond comes out of it here? These 3 bonds in the base, and there is one bond here. This one bond should repel, which is at 90 degrees, and these 3 are at 120 degrees. So this one bond should repel those at 90 degrees, because valence shell electron pair repulsion theory, all the pairs are repelling each other. If this is an angle of 120 degrees and this is an angle of 90 degrees, the repulsion would be quite high. So what happens as a result of this repulsion by this pair of electrons, these 3 bonds are pushed down slightly. And when they are pushed down slightly, they form, this is the shape that they form, the shape of a regular tetrahedron. It's a symmetrical shape, yes. It's a symmetrical shape, and it is known as the tetrahedral shape. Yeah. Now, this is such a shape that each angle, every bond here has an angle. Instead of 120 that was there between these now what happens, and this angle was 90. These 3 had an angle of 120 if it was a triangular planar. But by being pushed down, the 120 angle reduced, and each angle now becomes equal, and it becomes equal to 109.5 degrees. And now you can imagine this to be the triangle and this above it, or this to be the triangle and this here. In every direction, the shape of the molecule is the same. And these ends, if you join these, they form a shape which is known as the tetrahedron that I have done here. And imagine this to be actually on the surface of the sphere. These are all on the surface of the sphere. All 4 atoms are actually on the surface of the ball that I showed you. But if you make the geometry, what would the structure be like if you joined all the lines and you made the surfaces? The structure would be a tetrahedron. So this forms a regular tetrahedron when you have a molecule where you have 4 atoms around the central atom and all of them are identical, that is, all of them are bond pairs. You get a symmetrical structure which is known as the tetrahedral structure. And the 4 atoms occupy the corners of a regular tetrahedron, right? And if I just made the bonds of this molecule, examples are methane and the ammonium ion, carbon, H, 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 and H. So, and what's the angle? 109.5 degrees. Here all angles are 120 degrees. Do you see this? So we make the structure of methane, and methane would be 109.5 degrees. Let's move on to the next molecule now. The next molecule is where you have 5 atoms around the central atom. Now the central atom is being surrounded by 5 atoms. What did we see here? If you think in 2 dimensions, that is the initial reaction, you would imagine it to occupy the 5 corners of a pentagon, right? You would expect it to occupy 5 corners of a pentagon, and if you really see, the atoms are so close to each other, and if you see the angles here between the different bonds, each bond angle, if they occupied the 5 corners of a regular pentagon, would have been 72 degrees. But rather, instead of having this 5 corners of a pentagon, if we try to draw it in 3 dimensions, let us again come back to our triangular planar structure. And this time, what we did here was, we had a bond striking out of the triangle, the center here, one bond here, and the 3 were pushed down because of the repulsion by this bond. So what we do, we now have another bond coming out from this side, from the other side. Do you see this? From the triangle, now there are 2 bonds, one coming out from the front and one going out from behind. And now the repulsion from this bond to these 3 is equal to the repulsion of this bond to those 3 bonds. So the repulsion on both the sides being the same, this becomes the structure. It cannot, if the repulsion is the same, these bonds will not be pushed down or pushed up, because whatever push is being experienced by this bond to these 3, the same push is being experienced from under it. And therefore, this triangle now becomes fixed, the angles remain the same, it does not get distorted, and here one angle, one bond in front protruding out and one bond protruding behind it. That makes it a trigonal. Now, if you imagine, if this was a triangle surface, flat surface, and you tried to make a structure like this, you join these as surfaces, you would get a pyramid. Isn't it? If you have a triangle in the bottom, you have one face here, one face here, one face here, joining the tip here, that would form a pyramid. You remember the Egyptian pyramids? So now, instead of one pyramid, you can imagine with this bond here, you have one pyramid up here and one pyramid coming down, right? So there are 2 pyramids whose bases have been joined. You can imagine the structure to be somewhat like that. There are 2 pyramids whose bases have been joined. So this is the triangle in the middle, and this is one bond on top and one bond going under it. Do you see this? So if I had to make only the bonds of PCl5, phosphorus would be in the center, the chlorines, the 3 chlorines forming 3 corners of the triangle, and one phosphorus, one chlorine up here and one under here. This is forming one surface, but these 2 are not in the same plane. They are above and below, right? These 2 chlorines are above and below this planar surface. So this is, what is this? One pyramid is here and one pyramid is down here. So we call this a trigonal, that is 3 corners. The base has only 3 corners, and there are 2 pyramids, so we call it the trigonal bipyramidal shape. This shape is known as the trigonal bipyramidal shape. And what happened? How many pairs of electrons did we have around the central atom? We had 5 pairs, 3 occupied the triangle, and 1 above it and 1 below it. So we call, now this molecule has 2 types of bonds. One is the type of bonds that are falling along the, if you imagine this is along the equator, and these 2 would be along the axis. If you imagine this to be the globe, these 3 bonds are along the equator, and this is along the axis. These are axial bonds, right? So you have 2 types of bonds here. The straight ones are the axial bonds, and those which fall in the plane here, they are known as the equatorial bonds. And if you have 2 types of bonds, you also have 2 types of bond angles. The angles between the chlorines in the equator, that's a regular triangle. So what is the angle between these chlorines in the equator? It is a regular triangle. So the angle between these chlorines should be 120 degree. And what would be the angle of this axis here in the triangle? If this is the triangle and this is coming out, what would be the angle of this pencil with these 3 bonds? It is perpendicular. So the axial angles, that is the axial bonds, their angle is 90 degrees. So this angle is 90 degrees with all 3. It's a plane, and you have the pencil coming from the center. So all three angles are at 90 degree. All three equatorial angles or bonds are at 90 degrees from both the axial bonds. So this is the structure that is trigonal bipyramidal. And we now come to the last type of a symmetrical structure, that is the AB6 type. Now you have 6 atoms around the central atom. How would you imagine the bonds to be? Again, the two-dimensional imagination would be the corners of a hexagon. But the corners of a hexagon would make the central angles, each angle would be a 60 degrees. And that is very less. So we need another structure that could increase. Is there another structure that could be made which increases this angle? You remember, greater the angle, the greater is the distance, and lesser is the repulsion. Right? Our idea is to have structures where the angle increases. In this case, in the tetrahedral angle, why did we have 109.5? Because there were 3 angles that were 120, but one angle which was a 90. Which was causing the repulsion to all the other 3, and therefore this was distorted to form the corners of a tetrahedron. Now in this case, we see the hexagon doesn't help us. So just as we had the triangle and we had the 2 bonds coming off a triangle, if we now have a square, and the 2 bonds come out of the square, the center of the square. Now, in a square, all angles are 90 degrees, and this one has 90 degrees. This pencil is at 90 degrees to all these 4 bonds, and the pencil behind would also be at 90 degrees, which, if you imagine this like this, the pencil behind also is at 90 degrees to all the 4 angles. So, each of these is at 90 degrees to the other 4. These are at 90 degrees to these 4, the one in behind it also is at 90 degrees to these 4, and these 4 are also at 90 degrees to each other. And what did we have in a hexagon? Each angle was 60 degrees. Rather, now how would you imagine this in 3 dimensions, this structure? Now you have a square, and the square is the base of a pyramid, and this is the pole, and let us make the faces. This comes down as a triangle here, joins here, triangle here, joins here, triangle here, joins here. So you get a pyramid which has got 4 corners, right? So it is called a tetragonal pyramidal shape. It is a pyramid which has the base has 4 corners. But since we have another bond down here, you can imagine now 2 tetragonal pyramids which have been put joined, like base against base, they've been joined to make 2 tetragonal pyramids. So now what is the structure that you would like to imagine? These are 2 bases we have joined, imagine, and this is one and this is one pyramid. One pyramid pointing upwards and one pyramid pointing downwards. So we call it, this is known as the tetragonal bipyramidal shape. And you could, again, all these points, the 4 corners and this pencil and this, all the bonds are the same length. Why are they same length? Because they are actually occupying the surface of a sphere. So this shape, if you really see the tetragonal bipyramidal shape, is also known as the octahedral shape. So this is the octahedral shape, and the molecule of this type would be SF6. And if I only had to make the structures for SF6, I would make S, the 4 F's I would make as a square again, and these form an equatorial square and 2 axial bonds. For the sake of convenience, I make these slightly longer, or even if I made them the same length, they would have fallen outside this line. So there you have 2 axial bonds and 4 equatorial bonds. And each bond is a 90 degree with each other, and the axial bonds also have an angle of 90 degree with each one of these 4, and 180 with this, the other axial bond, but a 90 degree with each neighboring atom, you may say. So with each neighboring atom, the fluorines, they have 90 degree angle, which offers minimum repulsion. right? So these were the symmetrical structures according to the Vsepr theory. How do we determine the structures of these molecules? Now, Nyholm and Gillespie, they brought about the idea of the molecules which did not have such certain geometries, and their geometries were distorted. They explained them on the basis of difference in the repulsions between lone pairs, bond pairs, and lone pair, bond pair. So let us now do a few molecules which are distorted, and let's give a reason why they are distorted, right? Let us now study about molecules which have lone pairs in them too. And if there is the presence of lone pairs, then the lone pair repulsion is the greatest, lone pair, bond pair is less than that, and bond pair is the least. This fact has an effect on the structure of the molecules. So let us take our first example here. I have taken E as the lone pair and B are the surrounding atoms. So, and A is still the central atom. So we have a molecule of the type AB2E, which means that there are two atoms around the central atom A, and E means there is one lone pair, right? So you have this molecule. If you really make the structure originally, you have to imagine it that there are three atoms or three pairs of electrons around the central atom. So if there are three pairs of electrons, what would you expect? You would expect the structure to be a trigonal planar or a triangular planar structure where each angle is 120 degrees. Now comes into play the presence of the lone pair. But what do we see? Due to the presence of a lone pair, these atoms, they experience a slightly greater repulsion from this pair than they do from each other. So as a result of this, since this is a little stronger, it repels a little more strongly, it pushes these atoms slightly together. And when it pushes these atoms slightly together, instead of having, or rather we should say, you would expect the shape to be a trigonal planar, this becomes slightly bent, and this slight bent structure, the molecule, when you see the shape of the molecule, the lone pairs do not appear as an atom. So it is a pair of electrons, but in the geometry of the atom, in the molecule, you need atoms to be at places, and these are only electrons. So you will not see them when you try to study the structure of the molecule. So the molecule now appears to be just a bent molecule, and this lone pair of electrons is only influencing the shape of the molecule, but is not otherwise giving its own offshoot. It does not contribute, make a corner in the shape. So we have a bent shape of this molecule, and because of the repulsion of the lone pair bond pair repulsion, which is greater, the angle reduces from 120 degrees only slightly to 119.5 degrees, for example in sulfur dioxide. In sulfur dioxide, which is an example of this kind, or ozone, this angle reduces slightly because of the lone pair bond pair repulsion. Now we have the next type of molecule, that is AB3E. AB3E means there are four pairs of electrons basically, out of which one is a lone pair. So if there are four pairs, what would the regular geometry be? The four pairs of electrons, tetrahedron. So you would expect the shape to be a tetrahedral molecule, but one of these is a lone pair. So the lone pair is going to have its effect. All angles in a tetrahedral shape are 109.5 degrees. The presence of a lone pair pushes these slightly, thereby squeezing their angles. But in the molecule, in the actual shape, you will not be seeing this, you will only be seeing this. So when you see only this, what would you imagine this to be as? This would form the base of a triangle, and this is like it is protruding up from the triangle. So what would you imagine this to be as? It would be like a triangle, and from the center of the triangle you have A up here. This center appears to be, because these three bonds are downwards along it. So, or rather, let me show it to you with the help of these pencils. Now, in a tetrahedron, the fourth bond would have been here, but this is a lone pair. So now this appears to be a triangle, and this, if you make faces, this is just a trigonal pyramid. So it forms, instead of forming a tetrahedral shape, what we get is a trigonal pyramidal shape. An example of this kind of a molecule is ammonia, and it's a trigonal pyramidal shape, but the angle is not the tetrahedral angle. Due to the presence of the lone pair, the angle squeezes slightly to 107 degrees instead of 109.5 degrees, which is the tetrahedral angle. The next type of molecule is Ab2E2. Now, there are again 4 pairs of electrons around the central atom, but now instead of having one lone pair, there are 2 lone pairs and 2 bond pairs. So the regular geometry would again be a tetrahedral geometry, but the presence of these lone pairs, now there are 2, they are going to mess up even more. And how are they going to mess up? The 2 lone pairs have the strongest repulsion among each other. So the first thing they do is they repel each other more than they repel. And if they repel each other more, they come closer to the other 2. So they repel these 2 further away. So the shrinking of this bond will take place. These 2 in the final structure, these 2 are only acting as the repelling parties. They're not in the structure of the molecule. The molecule will only appear here. And it would appear to be a bent structure. The molecule would be bent. An example is water. In water, oxygen is in the center. It has 6 electrons in its outermost shell, and 2 of it uses to form the bond pairs with the 2 hydrogens, and there are 2 lone pairs. These 2 lone pairs push each other apart, and then each lone pair pushes the bond pair down and makes in the tetrahedral angle, and the angle comes down from 109.5 to 104.5 degrees, and the molecule is no longer tetrahedral because these 2 pairs of electrons are not contributing to the structure. They are only pushing, they are only repelling. So the structure of this molecule is called a bent molecule. The next type of molecule is Ab4E. In Ab4E, we have 4 atoms of one type and 1 lone pair. When you have 5, that is 4 plus 1, 5 pairs of electrons around the central atom, we just studied in the regular structures, you would expect this to be a trigonal bipyramidal structure. A triangle having 120 degrees each, and this is a 90 degrees, and these 3 bonds are equatorial bonds, and these 2 are axial bonds. That is what you would expect. Now, we find that instead of this structure, the trigonal bipyramidal, if you imagine this to be the lone pair of electrons and these to be the 4 angles, and you just now take this molecule and imagine a seesaw in a park. Shall I make the structure here? Or let me do it here. You know, when you go to the park, there's a support in the center, and there is a bar like this, and 2 kids sit on the seesaw, and one goes up and the other goes down in a seesaw. So this is somewhat like a seesaw structure. If you keep it like this would appear to be a seesaw. The molecule looks like a seesaw. So we say you would expect it to be a trigonal bipyramidal shape, but actually the molecule is a seesaw. But there is one more thing that you should know of here. Why was this lone pair of electron put here in the equatorial position? We could also have put the lone pair in the axial position. It was not necessary. We are only imagining the structure. So why do we imagine it to be here? Why do we feel logically it should belong here? And when we see the structure, it actually is a seesaw. It is not along the axis. And what is the reason for that is that if this lone pair, now I've made these 2 structures of this example. The example is SF4. SF4, in this molecule, in this structure, the electron is present, the lone pair is present in the equatorial position. And in this, I've made it in the axial position. Do you see this? Here it is axial and here it is equatorial. Why is the equatorial one correct is because here, or rather let me see the axial one. The axial is repelling these 3 bonds which are at 90 degrees to each other. It is repelling 3 SF bonds downwards. While here the equatorial one is pushing only 2 of these which are at 90 degrees to it. So the repulsion here is actually lesser in comparison to this structure. In this structure the repulsion itself is more. the structure itself is not as stable because we've arranged, did we say according to the Vsepr theory, the electrons try to occupy such a position that they have minimum repulsion and maximum distance. So this lone pair would not occupy the equatorial position, it would occupy the axial position. Right? So the right structure here would be this, and this is the structure of a seesaw. Right? The structure of a seesaw. So we call it the seesaw structure for this molecule. So let us now move ahead with a few more examples. Let us now do 3 more examples before finishing this topic. The next molecule is AB3E2. Now there are 2 lone pairs of electrons and 3 bond pairs of electrons around the central atom A. So since there are 5 pairs of electrons, the regular geometry expected would be a trigonal bipyramidal structure. But we find that this molecule, since it has 2 lone pairs, if we had lone pairs here at the axial position, again, since these 3 are at 90 degrees to the axial position, the repulsion would be very high. And this angle is 120, therefore the lone pairs would occupy the equatorial position. So these 3 lone pairs are here, the bipyramidal shape, this should have been, but in the actual molecule, you forget the lone pairs, and the molecules, if you see, what does this appear to be as? It appears to be, to look like the alphabet T. If you twist it like this would appear to be an alphabet T. So the actual molecule is in the shape of the alphabet T, and we say it has the T shape. An example of this kind of a molecule is ClF3. Now the question is again, why did we choose these to be the equatorial positions? Because if we chose, and why did we choose both the lone pairs to be at the equatorial positions? This is the structure that I just explained. The repulsion would be the least here because this is an angle which is 120 degrees, and this is where you could originally keep it at maximum distance. If we imagine that one of these lone pairs was kept in the equatorial position and one was kept in the axial position, then what would have happened? We would have distorted the triangle, and this would have pushed these 3 bonds downwards. And on the other hand, if we had this would only have repelled this and this and this. But this is at 90 degrees to 3 others, while these are at 120 degrees, the angles are more. Therefore, this is not so stable again. If you had both of them at the axial position, that would be the worst choice. Why? Because at the axial position, you're putting the lone pairs at an angle of 90 degrees from the other 3 bonds in the equatorial position. So you are actually not placing it where the repulsion would be the least. You're already starting with the position where the repulsion is the maximum. So you would not choose this either. So the best structure here would be one where you have both the equatorial corners being occupied by the lone pairs, and therefore the molecule should have the structure of the alphabet T. And we actually find this molecule, when we do the spectroscopy of this molecule, it does have the shape of the alphabet T. Right? So now, let us now predict the structure of this molecule, which has AB5E, one lone pair out of 6 pairs which are surrounding the central atom. If there are 6 pairs surrounding the central atom, what would the regular geometry be that you expect? You would expect a tetragonal bipyramidal, or which is also called the octahedral shape. So you would expect the molecule to be octahedral, that is 2 pyramids which have 4 corners, one over the other, one on top of the other, and one pointing downwards, one pointing upwards. You would expect it to be an octahedral shape. In the octahedral shape, all angles are 90 degrees. All angles are 90 degrees. So what would this occupy the position? This would not occupy a position in the square, because that would make it a little less symmetrical. Although the repulsion would be the same, yet it would make it a little less symmetrical, so we put it in the axial position. Now you have a square and a single square pyramid which comes up, because the lower pyramid automatically vanishes when the tip of the pyramid is gone and you're only left with the base. So you expected the molecule to be octahedral, but the actual geometry is square pyramidal. An example of this kind is BRF5. And the last example that we take here is of the type AB4E2. AB4E2, now there are 2 lone pairs. You will again expect 6 pairs of electrons around the central atom to have a regular octahedral geometry. But now, since you have 2 pairs and all angles are 90 degrees, if these 2 lone pairs occupy the plane, it would again be a distorted shape because it would appear to be like this. It would again form a seesaw-like structure, which is not required. A square planar is the structure where this would be the best, because these 2 pairs of electrons are now occupying the opposite ends. They are at 180 degrees to each other. So that is the maximum distance that you could give them. And these 4 are in the center. The repulsion from this side to the plane, or these 4 bonds, is equal to the repulsion from this pair, and therefore it has, on the whole, has no effect, no net repulsion for these 4, and they remain where they are, and hence the geometry of the molecule would be square planar. An example of this kind of a molecule is xenon tetrafluoride. So this was the valence shell electron pair repulsion theory. I hope you understood. If you found the video useful, please give it a thumbs up and subscribe to my channel, recommend it to your friends, and please keep returning for more videos in chemistry. Thank you for watching, and bye-bye for now.